third speaker in this session is Ange Song. He's a senior software engineer at Alibaba Cloud, who completed his PhD in 2022. His research interests primarily revolve around cloud networking protocols and architecture, as well as cloud-native applications.
Thanks for the introduction. Hi everybody, I'm Ange Song, coming from Alibaba Cloud. Now I'm introducing one of our research work, Canal mesh. Microservice needs application network functions such as traffic management, zero trust network, and observability. The traditional methods writing codes or using library in the business logic has limitations, such as language dependency, high maintenance costs, and low reusability. To this end, service mesh is proposed. The idea behind the service mesh is decouple the network functions from the application and move the functions to a generic agent alongside the application. We call the agent sidecar like this interesting figure shows. Service mesh allows the application to remain focused on business logic while the sidecar handles network tasks. But after deploying sidecar or proposed sidecar on Alibaba Cloud for 4 years, we have observed numerous deployment issues. The first is high intrusiveness and potential risks by embedding a sidecar into the user pod. The application and the sidecar coexisted. They share memory, lifecycle, controller, and so on. For example, the memory leakage in the sidecar may cause the app to crash. The second problem is performance degradation due to the extra steps introduced by traffic redirection to the sidecar. There are 2 extra context switch, memory copy, protocol stack processing are introduced. And the throughput and the latency are degraded by 3 times to 7 times. The third problem is excessive resource consumption of the sidecar. Based on our observation, for a large KBS cluster, the sidecar consumes thousands of CPU cores and thousands of gigabytes memory, and in extreme case, even much higher than that of user's application. Besides, the high control plan overhead for configuring so many sidecars is significant. Since each pod has 1 sidecar, and for cloud service, there may be hundreds of thousands of pods, so the numerous sidecar causing a high control plan overhead. And the configuration completion time and the southbound bandwidth overhead are proportional to the cluster size. So the high control plan overhead may cause configuration delays or even losses. There are existing solutions to solve these problems. First, Selim and Sprite use eBPF to embed the functions into the kernel and improve the performance and reduce the resource consumption. But due to the limited programmability of eBPF, they cannot support complex layer 7 functions, such as HTTP. Another solution is Mint. It adopts sidecar-less design. It decouples the complex layer 7 functions from the sidecar to a service-level shared layer 7 proxy and leave the layer 4 functions on the per-node shared proxy. Although Mint can somewhat alleviate the problems, but we think there are substantial room for improvement. Mint reduce the resource consumption for the users not want to using layer 7 by making it optional. But honestly, based on our observation, the optional layer 7 proxies offer limited value because, as shown in the table, the majority of users in our cloud want to use layer 7 rules in their service mesh. The second is incomplete decoupling. That means the layer 4 and layer 7 proxies are still in the user's KBS cluster, and the potential risks are still. The third is Mint didn't focus on the performance improvement. And the layer 7 proxy in the Mint are shared among the pods belonging to the same service, which experience synchronized peak and valley, which has a reduced peak shaving effect. The proxy in the Mint are proportional to the number of service and nodes. There are still numerous proxies that need to be configured, so the control plane overhead remains significantly. Based on the above analysis, we have the following 4 design goals. That is non-intrusive service mesh, improved performance, less resource consumption, and control plane overhead mitigation. To achieve these goals, our first design principle is deploying the proxy outside the user's KBS cluster. Through the fully decoupling, we can achieve non-intrusive service mesh. And the remote proxy deployment also reduces the twice layer 7 processing to once, which can improve the performance. The second design principle is service and tenant level proxy sharing. By the tenant level sharing can achieve efficient peak shaving, then reduce the resource consumption. By consolidating all proxies, the number of proxies needed to be configured is reduced to 1, which mitigates the control plane overhead significantly. Based on the above principles, there is a strawman architecture, that is consolidating all the proxies into a cloud gateway. But based on our experience, this strawman architecture has numerous deployment issues. The first is not all the functions can be performed remotely without any features losing. So the first open issue is how to achieve function equivalence. The second is due to the service mesh proxy are multi-tenant sharing. So how to solve the tenant isolation? How to achieve tenant isolation, such as to solve the virtual address overlap, failure isolation, resource contention, and so on. The third issue is the high capex of maintaining load balancer for multiple gateway backends and supporting high concurrent flows. Then we will show how we address the above issues of strawman architecture. To ensure function equivalence, we follow this basic principle. That is, offload functions to the remote gateway as much as possible, except for those who would negatively impact the user experience if conducted remotely. We assess the major features of service mesh if they can deploy it remotely, and show the results in this table. We take the traffic control as an example. The input of traffic control is the information in the packet header. And the processing logic of traffic control can be configured to the remote node by the controller. So we think the traffic control can be deployed remotely. Other details can be found in the paper. Based on the above tables, we design our architecture. We add to ensure function equivalence, we add a lightweight on-node proxy to serve minimal security and observability functions, and remains all other functions conducted remotely on the remote gateway. And to further reduce the resource consumption of the on-node proxy, we offload the asymmetric crypto of the on-node proxy and the gateway to a dedicated device. We call it a key server. So we have 3 components in Canal mesh: the lightweight on-node proxy for the minimal zero trust network and the minimal observability features, and the gateway for all the features, and a key server only for the asymmetric crypto. To ensure the high availability of the consolidating service mesh proxy, we configure each service across multiple AZ with multiple backends, and each backend has multiple replicas. In this way, Canal mesh can withstand sudden device or AZ failures and ensure that a service always has healthy backends available. To avoid packet header address space overlapping in multi-tenant cloud, we map VXLAN ID and inner 5 tuple to a globally unique service ID and attach it to the inner header. Then gateway can distinguish tenant service inside the virtual machine. While shuffle sharding can ensure a service always has a healthy backend available, but the traffic from the failed backends can temporarily overload the healthy ones, causing potential risks. To this end, we propose 3 response mechanisms. First, scaling, which is used for handling normal case in the gateway. We can scale in or out service backend list like this figure shows. Second, migration, which is used for anomaly case in gateway. We can update the list and migrate traffic to the newly added backends. Third, throttling, which is used for protecting users' KBS cluster. We may rate limit users' traffic at the gateway to prevent users' KBS cluster from being overloaded by hotspot. Next, we propose 4 anomaly detection mechanisms. To ensure sufficient resource for user service, we monitor resource utilization and performance metrics. If any resources are about to be exhausted or the performance becomes worse, we automatically scale their resource to prevent user experience degradation. Besides, we will also check for service level anomalies and migrate affected service to a sandbox. For the backend level alert, when a backend's worth level over a threshold, for example, the CPU, an alert will also be triggered. Unlike at the service level, we first need to identify the root cause service causing the increased load, and then execute scale or migrate for this service. When traffic patterns among services sharing the same backends are similar, we scatter these services by migrating some service to other backends to prevent the sudden CPU spikes. If the user's KBS cluster is hosted on our cloud, we monitor its resource usage in real time. If we see a sudden spike nearing 100%, we will discuss with the user whether rate limiting on the gateway to protect the cluster from being overloaded. The details and examples are shown in the paper. Each service has multiple backends and are different from other services due to the shuffle sharding. So therefore, we need to maintain per service load balancer and for traffic redirection. And to reduce the cost, we disaggregate the functions of load balancer like Beamer and conduct these functions on existing cloud infra. That is, doing load distribution on the router and session maintenance on a redirector in a backend. Such a cloud infra reuse allows us to achieve function equivalence of traditional load balancers with almost no additional cost. In addition to load balancers, sessions also consume substantial resources. After consolidating, our proxy needs to manage a large number of sessions. An imbalance between sessions and CPU usage is found. When the session is exhausted, the CPU utilization is only 20%. To address the resource usage imbalance of each replica, we propose session aggregation via tunneling. Then we will show the evaluation of Canal. Figure 1 shows the latency under LAT workloads. The latency of Canal is the closest to the no service mesh baseline and is much lower than that of ES2 and Mint. Figure 2 shows the latency under changing workloads. As shown in the figure, the throughput of Canal is much higher than that of ES2 and Mint. This figure shows the CPU core usage under changing workloads. Canal consumes much less user CPU resource than ES2 and Mint. Then we will show the control plane overhead improvement. As shown in the figure 1, the configuration time of Canal is much lower than ES2 and Mint for creating multiple pods. As shown in the figure 2, Canal's southbound bandwidth overhead is much lower than East2 and Min2. By aggregating sessions into tunnels after deploying redirector, cloud resource saving can further reach 55% to 70%. We also share the 4 years deploying proposed sidecar on our cloud and the 1 year of Canal deployment. There are many interesting experiences. For example, we have found that after consolidating, the healthy check traffic are much higher than that of user application traffic, even up to the 500 times. And we reduced the healthy checks by with the multiple level aggregation. And there are also many interesting experiences you can find in the paper. Then we will make a conclusion. We propose the first cloud-based multi-tenant service mesh for production deployment. The second, we present a production-validated system that addresses the issues due to remote deployment, service consolidation, and multi-tenancy. The last, we share our experience for deploying East2 on Alibaba Cloud for 4 years and Canal for 1 year. That's all. If you want to try Canal Mesh, you can email the second one. If you have more questions, you can email the first. Thank you.
We have time for a few questions.
You're now reduced that per node sidecar to be very simple, right?
Yes, thank you.
So can you now make that eBPF based? Because now you've sort of eliminated the worries about how complex it has to be.
No, not in the slides. We have used the eBPF already in our system. We redirect the traffic from the sidecar to the from the application to the on-node proxy by eBPF. It can improve the performance nearly, nearly 30%, I think.
Yeah,
So-
but that's the forwarding part. But even the sidecar function, you can now make it into eBPF for the.
We don't think so.
No.
I think the layer 7 features is so complex. The eBPF now cannot support.
But that you moved away, right? Right now, I'm talking about the per function sidecar that you have, which is very small.
Maybe.
Hey, this is Jinrong from Duke. So my question might not be technical. So what's the additional benefit you to the sidecar you bring to your customer, and how many customers are willing to migrate to your solution, and how many customers have actually migrated to Canal Mesh?
Okay. There are many benefits, such as the resource consumption is reduced much. We don't inject heavy proxy into the user's pod, so they buy the resource they buy can fully run their application. But in East2 and Mint, there are many resources are consumed by the proxy, like the proposed sidecar or the layers 4 and layer 7 proxy. And the southbound bandwidth overhead, that is the control plane overhead, is also mitigated by Canal Mesh. Yeah.
Yeah, and
So I think there are many benefits to migrate
you can
to Canal Mesh.
save the user CPU cost, but
Yeah.
how much in terms of cost do we actually save for them? Do we have any numbers? And how
No,
many
no,
customers
no.
have actually migrated?
The Canal Mesh is only deployed on our cloud for 1 year. We don't. It now purchased by many users, so it is free now.
Okay, thank you.
But you must have statistics on how much resources you have saved in your cloud, right?
Oh yeah, we save a lot on our cloud by the tunneling and the load balancer disaggregation. Yes, as shown in the, I think.
Yeah, that too.
As shown in this figure, we have saved. This cost is our cloud cost, not the users. Yeah.
I have a quick question about just the user interface for your users. When they are implementing or asking for service mesh functionality, is there like a fixed set of functions they pick from? Or can they actually give you any envoy filter or something? Like, what is is there a menu of choices given to them, or they can just bring in an arbitrary thing?
Oh, wait, are you asking how the user use Canal mesh?
Yes.
Yeah. It's just like Istio and Mint. You configure your service mesh and by an open API to our cloud. It's okay. It's just like what you use in Istio and Mint. It's the same.
So I can actually do any Envoy filters or not?
You just
Like,
can
because with
use the
Istio, I can do any Envoy filter if I wanted to, right?
You can do anything in your KBS cluster, but you can use the service mesh features we provided. Yeah.
So I guess that is a fixed set of features you're providing, or can I bring
No,
my own feature? Okay, got it.
It's same like Istio and Mint. They all provided some features they write in the documents.
Okay, let's take it offline.
Yeah.